It seems like every day we hear about LLMs getting better and better, not just at the things we kind of expect, like writing or summarizing, but at things that feel a lot more like genuine reasoning, like math or generating computer code.
Yeah, definitely. And that leap in capability, particularly when it comes to these complex reasoning tasks, well, that's something that's really been captivating researchers. And honestly, a major factor driving this progress is a technique called chain of thought, or COT for short.
Okay, so coaching of thought, we've touched on this before, but just for anyone who's new to this idea, could you give us a quick refresher?
Absolutely. So the core idea is that instead of an LLM just spitting out a final answer, it's prompted to generate a series of steps. It's almost like showing its work like back in math class. And what's really interesting is that this often seems to unlock much more advanced problem-solving abilities.
So it's like guiding the model to break down a complex problem into these smaller, more manageable pieces, and it generates a sequence that kind of looks like logical steps leading to the solution.
Exactly. And this has led to some pretty remarkable improvements in tasks that really require that kind of multi-stage reasoning.
Which leads to this question that I always find so fascinating, like, why does this seemingly simple approach work so well? I mean, you could just tell the LLM in the prompt, think step by step, which is called zero-shot code, or even give it a few examples of reasoning, even if they're not perfect, which is few-shot code, and it's like its performance just jumps up a level. It's a bit counterintuitive, right? If you tried to learn efficiently, you'd think the most direct route would be the best.
Yeah, you've hit on a really important point, and that's actually exactly what this recent paper, Chain of Thought Empowers Transformers to Solve Inherently Serial Problems, aims to explain. And they're trying to get at it from a really fundamental level by looking at the idea of expressiveness.
Expressiveness, now that's a term we encounter a lot in computer science, but for someone who maybe doesn't have that background, could you break down what it means in this context?
Sure. So you can think of expressiveness as the inherent ability of a system, in this case, a transformer model, to solve certain types of computational problems. And what researchers are trying to figure out is what kinds of problems these models can fundamentally handle, both with and without this chain of thought mechanism.
So it's not just about the size of the model or the amount of data. It's about something deeper in the way it's structured and how COTI interacts with that structure.
Exactly. To really get at this, the paper dives into some concepts from theoretical computer science, specifically circuit complexity. Now, I know that might sound a little intimidating, but the idea is actually pretty intuitive. We can think of these circuits as a way to model how computation flows within the transformer.
Okay, so circuit complexity, it's like we're looking at the very basic building blocks, the equivalent of logic gates in a computer, and trying to understand what these models can and can't compute efficiently.
Yeah, that's a great analogy. The researchers use this framework to try and establish what the fundamental computational power of these transformers actually is. And the paper specifically looks at what are called constant depth transformers, which are transformers that have a fixed number of those processing layers.
And what was our understanding before this paper about what these standard constant depth transformers, the ones without COT, were capable of?
So previous research had shown that these types of transformers are really good at parallel computation. They can handle problems that can be broken down into lots of independent steps that can all be executed at the same time. In the language of circuit complexity, they were shown to be capable of solving problems that fall within a complexity class called TC0.
Okay, TC0. And remind me what kinds of problems are in that category.
So TC0 includes problems that can be solved in constant parallel time using circuits with specific types of logic gates, like and or not gates, and even a more powerful type called the majority gate.
So they're good at tasks where you can look at a bunch of information at once and make a decision based on the overall picture.
Exactly. But here's where this new paper introduces a really critical and innovative point. It considers the impact of finite precision in the calculations. You see, real-world LLMs don't work with perfect infinite numbers. They use approximations like 16-bit or 32-bit floating point numbers. And when you factor in that more realistic constraint, our understanding of their capabilities starts to shift.
So how does this limited precision change what these transformers can fundamentally do?
Well, the paper establishes a new and stricter upper bound on their expressiveness. They show that when you have this more realistic constant bit precision, constant depth transformers are actually even more limited than we previously thought. They can only solve problems within a smaller complexity class called ACO, which is a subset of TCO.
And the key difference is that ACO doesn't have that powerful majority gate, right?
You got it. And while that may seem like a technical detail, it actually has big implications for the types of problems these models can handle efficiently. For example, the paper explains that a constant precision transformer without COT probably can't even reliably figure out if the number of ones in a really long sequence is even or odd. That's called the parity problem. And tasks like that generally require something like that majority function to be solved efficiently in parallel.
Huh. So even for something that seems pretty basic, like checking for even or odd, these models in their standard form would struggle. Now, what makes this new understanding, this ACO bound, more accurate than the previous TCO view?
Well, the key insight is in how floating point numbers behave during computation. Unlike ideal arithmetic, each floating point operation introduces a tiny rounding error, and the paper highlights how this immediate rounding makes things like addition not strictly associative anymore. For instance, if you round the result of adding three numbers in different orders, you might get slightly different answers, and this seemingly small detail can actually have a big impact over many layers of computation.
Right, those little rounding errors can build up and fundamentally change the outcome. So standard transformers with realistic precision, they're kind of like a less powerful parallel computer than we initially thought. Now let's bring chain of thought back into this. How does this sequential process change those fundamental limitations?
This is where things get really interesting. The paper's main hypothesis, which they back up with some rigorous arguments, is that qt essentially empowers transformers to perform inherently serial computations. These are computations that by their very nature have to happen step by step, where the result of one step feeds directly into the next, as opposed to everything happening at once in parallel.
Serial versus parallel, that's a crucial distinction. So tasks that have this natural sequence of steps where you can't just jump to the end without going through those intermediate stages, those are the ones that would be really tough for a purely parallel system.
Exactly. Now, without qt, the number of sequential steps a constant depth transformer can handle is limited by its fixed depth. That's the number of layers it has. But with qt, where the model generates, let's say, t intermediate tokens, the potential for serial computation increases to t. And what's really important is that t can actually scale with the length of the input, unlike that fixed depth. It can do a varying number of steps depending on the task.
So if a problem needs a sequence of logical steps, chain of thought allows the transformer to sort of simulate that sequence internally, and that bypasses those limitations of its parallel architectures, like it can run algorithms that require steps.
Exactly. It's not just giving the model more space to think, it's fundamentally changing the kind of computation it can do. And the paper actually formalizes this by defining a new complexity class, specifically for models using CIS. They call it CISERN, SEN. This basically describes problems that can be solved by a constant depth transformer with a certain number of TA steps, TRN, and a certain precision for its numbers, SN and EN.
Okay, so that's their way of capturing the power of TI mathematically. And what's the big theoretical result they'd be able to prove using this framework?
The really cool finding is that with just a relatively small embedding size that grows kind of slowly with the input, a constant depth transformer can solve any problem that can be solved by a Boolean circuit of a certain size by using that same number of chain of thought steps. It's a huge boost in expressiveness.
So it goes from those limitations of AC0 to being able to simulate any circuit of given size with enough COT steps. It means chain of thought isn't just about giving the model more room for work, it's enabling a whole different type of computation. It's like it can run any algorithm that can be expressed as a sequence of logical steps.
Exactly. And the key takeaway is that it's not just what is in those intermediate steps, it's the actual act of generating them one after another that makes this possible. That's the innovation.
Now, the paper also backs this up with some actual experiments, right? It's not all just theoretical.
Oh, yeah, absolutely. To test their theory, they looked at four core problems. One was modular addition, which we know is easy to parallelize and falls within that TC0 class. But the other three, permutation, composition, iterated squaring, and something called the circuit value problem. These are all thought to be inherently serial, meaning they're much harder to do with just parallel computation.
So they're like testing grounds for this idea of serial versus parallel. And what happened when they ran these experiments?
Well, just as their theory predicted, the standard transformers without using CoT really struggled with those three serial tasks. They either needed a crazy number of layers to get decent accuracy, or in some cases, they couldn't solve them at all.
But when they used chain of thought on those same tasks,
They saw a huge improvement in accuracy even when using transformers with just a few layers. It was really striking empirical support for their idea that CoT unlocks this more powerful serial computation.
they even did something called a hint experiment, right? What was that all about?
Yeah, that was really clever. To really isolate the effect of the sequential generation process, they tried giving the model the correct intermediate values directly as inputs, basically like hints, but without having the model generate those steps itself. And what they found was that this hint-based approach didn't work nearly as well as having the model actually go through the process of generating those steps with COTI. So it really shows that it's the process itself that's key, not just the information in those steps.
That's fascinating. It highlights how novel the COTI mechanism really is. So, stepping back a bit, what would you say are the biggest contributions of this work from an academic perspective?
I'd say there are a few key innovations. First, their analysis of transformer expressiveness under the constraint of finite precision is a big departure from a lot of prior work. By grounding their analysis in the real-world limitations of here computers represent numbers, they give us a much more accurate and relevant understanding of what these models can actually do.
And they also use some pretty advanced theoretical tools, didn't they?
Yeah, they cleverly applied concepts like the Krohn-Rhodes decomposition theorem from automatic theory to formally prove those upper bounds on the expressiveness of finite precision transformers. It's a pretty sophisticated way of connecting different areas of theoretical computer science.
So, really bridging the gap between theory and practice. Were there any other big theoretical breakthroughs?
Yeah, they established what are called separation results. For example, they showed that a certain problem, which is thought to be solvable with COT, is very likely not solvable by standard constant depth transformers without COT. So they formally proved that COT adds computational power. It's not just a hunch.
And what about the size of those embeddings? We talked about how a slowly growing embedding size is enough for simulating Boolean circuits. Does a larger embedding dimension give you even more power with COT?
That's a great question, and the paper does look into that. They found that while a small embedding size is enough to get the benefits of COT for simulating those basic circuits, larger embeddings combined with COT might let you simulate circuits with even more powerful types of gates directly. However, their analysis suggests that to get the full power of really large circuits, you don't necessarily need to go beyond those small embeddings if you have enough COT steps. So there's a trade-off there.
And they also talked about this thing called the circuit value problem, or CVP, which is a classic problem in computer science. What's the connection there?
Right, so CBP is a problem that's considered really hard for parallel computation, and the fact that transformers with COT can handle it suggests that COT lets them overcome some of those inherent limitations of parallel processing. It's like COT lets them tap into a different, more powerful mode of computation.
So, to sum it all up for our listeners, what's the most important takeaway about chain of thought, especially in light of the new insights from this research?
I think the biggest takeaway is that chain of thought isn't just a clever trick. This research provides a solid theoretical foundation for understanding why it works. It fundamentally changes what transformers are capable of by allowing them to perform these step-by-step computations, which are normally really hard for them, especially with the limitations of real-world number representations. It really expands their ability to solve more complex reasoning problems.
It's like an aha moment where we realize that the way those intermediate thought steps are generated sequentially is just as important as what's actually in them. It's a whole new way of thinking about how these models compute.
Exactly. And this deeper understanding is going to have a big impact on how we design and use LLMs in the future, particularly for things that require complex reasoning, problem solving, and even the kind of sequential logic that's at the heart of a lot of science and engineering.
It makes you wonder what other cognitive processes we might be able to unlock in AI with similar mechanisms that encourage that sequential processing. It feels like we're just starting to scratch the surface of what these models are truly capable of.
For sure. And for listeners who want to dive deeper, I'd recommend checking out some of the fundamental concepts we talked about, like circuit complexity and automated theory. And of course, the paper itself is a great read. It's really pushing the boundaries of AI research.
It's a truly mind-blowing exploration of the power of sequential thought in artificial intelligence. And it gives us a lot to think about regarding the future of AI and its ability to solve increasingly complex problems. Thanks so much for breaking all this down for us.
It was my pleasure.
Well, folks, that's all the time we have for today's deep dive, but the exploration doesn't have to stop here. Keep that curiosity burning, and we'll catch you next time.